Welcome to the last session of the course of differential equation. In this differential equation, we also discuss about the some applications of the first order differential equation. In the last session, we discussed about the orthogonal trajectories, how can we find the orthogonal trajectories of the given family of curves that we discussed by using the concept of the first order differential equation. Here we will discuss about the growth and decay. In many natural phenomena, quantities may grow or decay at the rate of proportional to their size, and on that case, for example, if y is equal to y of t, the number of individuals in the population of the animals or bacteria at a time t, then it seems reasonable to expect that the rate of the growth y dash of t is proportional to the population y of t, that is y dash of t is equal to k y of t for some constant k. See, my dear students, the mathematical model given by the equation y dash of t is equal to k y of t can be predicted what actually happens fairly accurately under ideal conditions. See, my dear students, that is unlimited environment is there, adequate nutrition is there, immunity to disease, these are all the consideration on the case of that questions. So, see, also we can see many examples in nuclear physics, also chemistry and finance also we will discuss the concept of the growth and decay. So, my dear students, in general we can say that if y of t is the value of a quantity y at a time t, and if the rate of change of y with respect to t is proportional to the size y of t at any time t, then we can write this as dy by dt is equal to ky. Now, we got this is the equation number 1. See, this represents the growth and decay. In this growth and decay, the this is actually a differential equation, that is the first order differential equation. See, my dear students, where k is a constant, this equation 1 is sometimes called law of the natural growth, that is if this constant value whose value is greater than 0 or sometimes maybe the value may be less than 0, on that case we can say that that is the law of decay. So, this is the law of exponential growth, sometimes maybe the growth is not linear, that may be exponential, on that case we can say that the exponential growth and decay can be written as y is equal to c e raised to k t. Here c is a constant and k is a constant, they are the arbitrary constant. C is the initial value that can be found from the initial condition y of t naught is equal to y naught. K is the constant of the proportionality which can be found from additional condition which might be given in the problem, that might be given in the problem. Now, come to a note that the note in this note we discuss it is that if k greater than 0, then the exponential growth occurs, and as we discussed before, if k greater than less than 0, then the exponential decay will occur. Okay, my dear students, to prove that, let us take some initial time quantity is known and is y of t naught equal to y naught, that we discussed in initial value problem. Here we have initial condition is y of t naught is equal to y naught, where t naught is the initial time, then the differential equation dy by dt is equal to ky. My dear students, you may consider is separable differential equation. Okay, is separable differential equation, and then we can solve it as we done in our first order differential equation. Firstly, we discussed about the method of variable separable, like that this is a separable equation, through that way we can solve this differential equation. See, dy by dt is equal to ky, therefore, dy by y we take this y to here and dt to here. So, we will have dy by y is equal to k dt. So, integrating both sides we will get integral of dy by y is equal to integral of k dt. So, dear students, we will have integral of dy by y is a log y is equal to derivative integral of k, that is k t, plus the constant of integration c is there. So, we took the exponential function on both sides. So, e raised to log y is equal to e raised to k t plus c. So, finally, we will have y is equal to e raised to log y is equal to y, this is equal to e raised to c into e raised to k t is there. So, dear students, we will have this is equal to y is equal to e raised to c into e raised to kt. So, then we just rewrite this y is equal to c1 e raised to kt, where c1 is equal to plus or minus e raised to c that we mentioned here. Okay, fine. Now, using the initial condition, we can apply the initial condition in this questions. So, we will have y of 0 equal to y naught is here. So, y of 0 is equal to y naught, that means t naught is equal to 0 and then y is equal to y naught. So, y of 0 equal to y naught is equal to y naught, that is come to the this one here, this is a y naught is equal to c1 e raised to k into 0 is there. So, dear students, c1 e raised to k into y naught is equal to c1 e raised to k into 0 e raised to 0, that is y naught is equal to c1. So, y is equal to the value of c1 is equal to y naught that we found, and therefore, y is equal to y naught e raised to kt is there. That is the solution. Now, to find the additional constant k, we need additional condition. We have one more constant is here, that is k is here. Based on that k, we understood whether it is growth or decay. So, we need two additional condition that which might be given in the problem. While for a particular problems, we will have a condition to find the value of k. So, my dear students, come to example. In example 1, we will discuss a certain culture of bacteria grows at a rate of proportional to its size. If the size is doubles in 4 days, if the size is doubles in 4 days, find the time required for the culture to increase to 10 times of its original size. Dear students, actually here given it is that to double the size it will took 4 days. Now, our task is that how many days it is needed for the culture to increase 10 times, okay, to its original size. Okay, fine. While solving this problem, let us p of t. P of t be the size of the culture after t days. We discussed a function as p of t is the size of the culture after t days. So, my dear students, their rate of change, rate of growth or decay is actually, as we did before, this is instead of dy by dt, here we have dp by dt is equal to kp. So, dear students, dp by dt is equal to kp. We will use the initial condition p of 0 equal to p naught, as we done before, y of 0 equal to y naught. Here we have initial condition p of 0 equal to p naught. See, dear students, so have to find the arbitrary constant. Have to find the arbitrary constant. So, we will find the additional constant k by using the additional conditions. So, here we have given it is that the additional condition as p of 4, it will double from the initial condition after 4 days. If t is equal to 4 after 4 days, the initial value will be doubled. P naught is the initial status of that bacteria. Okay. So, we have this is equal to p of 4 is equal to 2 p naught. Now, here we have p is equal to c e raised to k t, that we can found from here by integrating. We can found from here, this is equal to, from here we will get p is equal to e raised to k t, that is equal to p is equal to c e raised to k t is there. While solving the differential equation, we will get solution like this. So, from the initial condition we have p of 0 equal to p naught. Okay. P that is whenever t is equal to 0, the value of p is equal to p naught. Okay. So, we will have the arbitrary constants. This we have p of 0, p naught is equal to c, come to the value here c p naught, p of 0 equal to p naught, that is p naught is equal to c e raised to 0 is there. So, we have the p naught, c e raised to 0 is 1, therefore, c is equal to p naught. See, dear students, now we found c is equal to p naught. The value of p naught, c is equal to p naught, that is the initial status of the bacteria. So, from the so we found from here, hence we have here is equal to p is equal to c e raised to k t is there, that is p is equal to p naught into e raised to k t. P naught is the initial value. So, we have additional condition is there, that is p of 4 is equal to 2 p naught. Whenever t is equal to 4, we can find the additional constant k. So, 2 p naught. See, dear students, whenever p of 4, the value of 4 is equal to, whenever t equal to 4, the value of p is equal to 2 p naught. So, we can replace that is to here in this question, that is equal to, here we can replace that value. See, my dear students, here you can replace p of 4 is equal to 2 p naught is there. Therefore, c e raised to, instead of c we found p naught e raised to k into, that is actually k into the value of t equal to 4. So, finally, we will have here, this is the, just a minute, yes, 2 p naught is equal to p naught e raised to k t. So, the value of t equal to 4. Therefore, 2 p naught is equal to p naught e raised to 4 k is there. Now, dear students, we can find, we can cancel p naught and p naught, e raised to 4 k is equal to 2. We can take the logarithm on both sides. So, log e raised to 4 k is equal to log 2 is there. So, log and e is there, therefore, 4 k is equal to log 2, okay, 4 k is equal to log 2, therefore, k is equal to log 2 divided by 4. So, we understood that have the value of the approximately equal to 0.173. So, thus the time required for the culture increased 10 times to its original size can be found by using, we already got the value of k and we got the value of c, and we have the function p is equal to say p naught e raised to k t is there. So, we found the value of k from here, that is approximately equal log 2 divided by 4, that is approximately equal to 0.173. So, we can find the time required for the culture to increase 10 times to its original size can be found from by using 10 p naught is equal to p naught into e raised to value of k is equal to 0.173 t that we found. Okay. So, 10 times of p naught, that is the 10 times of the initial culture is there. So, p naught is the initial culture, that is equal to, from here we can cancel p naught and p naught, finally, we have e raised to 0.173 t is equal to 10. We can take the logarithm on both sides. So, while taking the logarithm on both sides, we will have e raised to 0.173 t, log of e is there, and log and e will go on, and finally, we have 0.173 t is equal to log 10. So, therefore, t is equal to log 10 divided by 0.173. So, finally, t equal to log 10 divided by 0.173. So, while evaluating that, t is approximately equal to 13.31 days. So, that means it is required 13.31 days to grow 10 times from the initial culture. Okay. Now, dear students, that is the way. See, actually what we did here, you may go back to the question, actually we need to how many days it will require to grow the culture 10 times then now. So, actually what we did here, it is that we got the solution as p of t be the size of the culture. After 3 days, we will have the differential equation is there, we will apply the initial condition. After applying this initial condition, we have additional condition is there, after 4 days it will be double from the initial culture. The initial culture is p naught is there, therefore, p of 4 is equal to 2 p naught is there. Therefore, we will have this is equal to p is equal to c raised to k t while evaluating, and we can find the value of c. Okay, c is equal to p naught. So, we rewrote this equation as p is equal to p naught e raised to k t is there, and we have addition condition after 4 days it will be double. So, while applying that one we can evaluate the value of k. So, now we found the k is approximately equal to 0.173. So, we just applied that one 10 times of initial culture is equal to like this. From there we can find the t. So, while manipulating that equation we will get the value of t, and now we found the t as 13.31 days to grow this culture 10 times. Okay. Now, dear students, come to the next example. In this example we will discuss about is the fact that the world population was 2560 million in 1950 and 3040 million in 1960. To model the population of the world in the second half of the 20th century, assume that the growth of rate is proportional to the population size. What is the relative growth rate k? Use the model to estimate the world population in 1993 and to predict the population in the year 2020. We already passed 2020, but even though what is actually we will have an opportunity to compare actually what the population in here in all around the world based on this population. So, we have to make a different model. That model we already given the data like in 1950 we have the population, the world population was 2560 and in 1960 it is 3040 million. So, the that is actually what is we can how can we create a mathematical model using that we can predict how many number of peoples are there in the world at the year 2020, and also you can forecast by using that model you will get some error, you can have some error analysis. After analyzing the errors, finally you are able to expand this model. What about the population of the world after 2030? Like that we have many much possibilities are there if you found a model. So, just we go to the solution. We measure the population p of t in millions of peoples, p of t as a population function. We have, as we did before, dp by dt is equal to kp. From here we can solve, this is equal to dp by p, log p is equal to k dt. While integrating that one, log p equal to kt plus c is there. While manipulating that one, finally we will get the solution as p is equal to c e raised to kt is there. See, dear students, so we have the initial conditions, p of t naught is equal to p naught, that is p of 0, p of t naught, p of 0 equal to 2560 millions. Okay. Thus we can find the arbitrary constant by using that concept. So, my dear students, we are able to find out p of t, p is equal to c e raised to kt, p of 0 equal to c e raised to 0, p of 0 equal to 2560, okay, fine, 2560, that is equal to c. Okay. Now, the value of c is equal to 2560. Okay. Now, we will find the additional constant. Now, we have one more constant is there, with that one k is there. So, like that we already discussed, based on the value of k we will discuss whether it is growth or decay. Okay, fine. We can forecast, we can predict that is definitely that will be the growth. Now, we will find the additional constant k by using the additional condition, that is p of 10. After 10 years, in 1950 it is the population is 2560. After 10 years 1960 the population is actually 3040 millions. So, p of 10 is equal to for 3040, that is the additional condition. We already have p is equal to c e raised to kt is there. Now, p of 10 is equal to 3040, therefore, 3040 is equal to the value of c, that is we found 2560 is there, e raised to 10 years are there, 10 k, the t is equal to 10. Okay, Fine, that is e raised to 10 k is equal to 3040 divided by 2560. So, log of e raised to 10 k is actually log of e raised to 10 k is actually we can find 3040 divided by 2560, that is actually log of e raised to 10 k is equal to log of 1.1875 is there. Okay, dear students, that is equal to you can apply the log and e is there, therefore 10 k is equal to log of 1.1875 is there. Now, my dear students, you are able to find the value of k. Now, k is equal to log of 1.1875 divided by 10 is there, that is actually approximately equal to 0.01785. Okay. So, you can evaluate by using the calculator, you will get the value like that. Okay. Fine, my dear students, now we found the value of k. Now, we can rewrite our equation as this is actually 0 point, you can multiply this one, this with 100. Now, we can find this is equal to the relative growth rate is about 1.7 percentage per year, and the model is actually p of t is equal to. Now, we found the model, we modeled a function how based on where t stands for the years, and you can find the population function as p of t is equal to the 2560 into e raised to 0.017185 into t. Okay, you can calculate. Okay, fine. Now, we estimate that the world population is in 1993 was by using this model. We already found the population predicted by using this model. So, we have the formula p of t is a function like this. Now, dear friends, this population function we can find p of 43. Okay. We started from 1950. Okay. 1950. Now, after 43 years in 1993, you can estimate this is approximately equal to, instead of t we just replaced as 43. Okay. We started 1950 plus 43 is 1993. So, in 1993 they approximated the population as 5,360 millions. See, my dear students, after this one 2020, from 1950 to 2020, it will took 70 years. After 70 years, the value of t is actually, the value of t is actually 70. In 2020, the model predicts that the population in 2020 will be that is p of 70. Our initial year is 1950. From 1950 to 2020, it will have 70 years are there. Therefore, t is equal to 70, p of 70 is equal to 2560 into e raised to 0.017185 into 70. You can evaluate, you can calculate by using calculator. So, definitely that value is approximately equal to 8,524 million peoples are there in the world according to this population growth model. Okay. Find the the model population growth in the second half of this 20th century, that is actually this is the graph of the population model. Okay. Fine. So, the approximately these both are equal, no problem. Now, we have I am providing one question to as your exercise questions. See, in this exercise we discuss the population of a town at a rate proportional to the population size at any time. It is initial population of 1000 increases by 10% in every 5 years. Okay. What will be the population after 50 years? I am providing a hint as p of 0 as the initial condition, p of 0 equal to 1000, that is the initial population, and p of 5, that is the 1000 plus 1000 divided by 10, that is actually the value is equal to 1100 is actually p of 5. So, my dear students, we have one more example. Just this you may do this example as also exercise question. I am providing this one radioactive decay. The radioactive material has an initial mass 100 milligram. After 2 years, it is left to 75 milligram. Okay, the 25 milligrams is decayed. So, find the amount of the material at any time. What is the period of its half life? So, we can find the radioactive decay half life period of the this radioactive element. Now, see, while evaluating this solution, we can find dy by dt is equal to ky. As we done before, the solution is like that, y is equal to c raised to k t is there. The same thing will happen, y of t naught equal to y naught, y of 0 equal to initial year, it half 100 milligram is there. Okay. So, finally, we can find the value of c while applying this. Now, we found c is equal to 100. So, my dear students, y is equal to 100 e raised to k t is there. You can find the value of k. Okay. With the additional condition that we already given after 2 years. Y of 2 is equal to 75 milligram, it is decayed 25 milligram, and 75 milligram is equal to after 2 years, therefore, 100 into e raised to t is equal to 2k is there. So, here we will have e raised to 2k equal to 75 divided by 100. Okay. This is equal to log e raised to. Okay. We can take this is equal to 10k, e raised to 10k is equal to, this is equal to log of 0.75 is there. So, finally, we will have this is equal to 2k equal to log of 0.75. Now, finally, we will have k is equal to log of 0.75 divided by 2, that is equal to negative of the 0.1438. See, here the value of k is actually negative. So, whenever value of k is less than 0, instead of growth the decay will happens. Okay. Thus, we have y of t is equal to, we found a model, that is a function y of t is equal to 100 into e raised to minus 0.1438 t. This we found that model. So, actually we need to find out the half life period, that is the 50 milligram whenever y is equal to 50 milligram. So, I have to find the value of t whenever the value is equal to the y is equal to 50 milligram, that is 50 is equal to 100 into e raised to minus 0.1438 into t. So, e raised to minus 1438 t is equal to 0.5. Finally, we have log of e raised to 1438 t is equal to log of 0.5. So, finally, we will have this is equal to log and e will gone, finally, minus 0.1438 t is equal to log of 0.5. So, t is equal to log of 0.5 divided by minus 0.1438 is actually 4.82 years. That means, approximately equal to 5 years to remains half of the material. Okay, dear students, I am providing one more exercise. I just ran through this question very speedily, but very simple. You can do that by yourself as an exercise also. One more exercise question I am providing as this is equal to, initially there will be 100 milligram of radioactive substance present. After 6 hours, the mass is decreased by 3%. If the rate of the decay is proportional to the amount remaining after 24 hours, determine the half life of the radioactive substance. Okay. You may try to find many questions from your this one chemistry and physics materials, many engineering problems you can find from the social science and population studies everywhere, and in case of the biological science also you can find such questions. That is very nice and simple applications of the first order differential equation. So, try to find more and more questions and try to solve it, and you may try to develop a simple mathematical models. It will be really motivate you. Okay. Thank you for watching these videos. Thank you very much.